Hello. In this video, we're going to be going over what it means for a complex valued series to be absolutely convergent. We're then going to go over using the ratio test to test for absolute convergence, and we're going to see an example. So let's get started. A complex series is absolutely convergent if the real series, where we take the modulus of each of the terms, is convergent. Now, note that some things to note. Absolute convergence implies convergence. So all series that are absolutely convergent must be convergent. However, convergence does not imply absolute convergence. There exists series that are convergent but not absolutely convergent. Okay, now, one of the ways to test if an infinite series is absolutely convergent is the ratio test. So what we're going to do is we're going to take the limit of the modulus of the ratio between consecutive terms of the series as the limit as the index goes to infinity. And if this limit is less than 1, then we conclude that the series must be absolutely convergent. And by extension, it must be convergent. So we're going to try and apply the ratio test with an example. We're going to take a look at this infinite series. Okay, so the ratio test is going to ask us to find the limit as n approaches infinity of the modulus of I n plus 1 over 3 n plus 1 divided by I n over 3n. So first let's do some simplification here. So we can say that this is equal to, so we're seeing if this is less than 1. If this is less than 1, then we know that this is absolutely convergent. So, okay, we can take the modulus outside. So we can write this like this. Divided by over 3. And this is the same as plus 1, so timesing the flip of that, so 3n over 3n plus 1 by n. Okay. And so we can just figure out the modulus of these. So, okay. So this is the limit as n goes to infinity. I to the power of n plus 1 divided by I to the n is just going to be I. And then 3 to the power of n over 3 to the power of n plus 1, that's just going to leave 3 down here. So now the n is gone, essentially. So we can read the limit. The modulus of I is just 1, and the modulus of 3 is just 3. And so the limit is 1 over 3. This is less than 1, and so this series up here must be absolutely convergent, and by an extension, convergent, as the ratio test says. What we computed was L, and it was less than 1, because it was 1/3. Now, one thing to note about absolutely convergent series is that if a series is absolutely convergent, if an infinite series is absolutely convergent, we can rearrange the terms in the sequence without changing the summation itself. Now this seems quite obvious. So for example, we have z0 plus z1 plus z2 da 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 zn plus zn plus 1 dot dot dot. We can, if this series is absolutely convergent, we can read it back to front. For example, we can do zn plus 1 add zn add z2 add z1 add z0, and this wouldn't change the value of the summation. Now this might seem trivial to you because, you know, order shouldn't matter when it comes to summation, but because it's an infinite series, it's infinite summation, order does matter. So if a series isn't absolutely convergent, we cannot rearrange the terms and get the same value. But if it is, we can. So that's why a series being absolutely convergent is quite an important property. And we'll see that when we're looking at the Maclaurin series for functions like e to the x and so on. But no, thank you for watching the video. Any questions, please leave them in the comments below.